So today's session we are going to see the second module of the basic electronics. Okay, so the second module basically deals with your digital system. So before going on to the topic, what is meant by digital system? So the digital system mainly deals with two inputs, that is 0 and 1, right? Okay, so the digital system can be based on or can be divided into different hierarchy. So starting with the level 1, which consists of electronic components like transistors, resistors, capacitors, both active as well as passive components. That was your components level, which you have already studied in your module 1. Okay. So these components will be embedded onto your second level, that is called as your functional, which consists of functional logic unit or your basic gates. Okay. Gates, basic gates, universal gates, etc., which forms the first level of your integrated circuit, that is your small scale integration. Moving on to the next complex level is your level 3, which consists of your adders, subtractors, multiplexers, which forms your medium scale integration and large scale integration. And more complex, the level 4 will be your very large scale integration, which the example is your microprocessor. So basically after that the level 5 consists of more complex unit. Okay, so basically you are going to your unit deals with your second module to your second level to your fourth level. So starting off from the basic digital concepts to your four topics, that is logic units, then your data representation, realization using gates, shift register, and so on. Okay, so moving on to your first topic is called as your logic gates. Under logic gates you are going to study the different basic the different types of gates available. Okay, so as per your syllabus, the only thing which is required is the logic circuit and the working principle along with truth table. Okay, so starting off your first subdivision in logic gates, you are mainly studying 7 different gates. Okay, so what are the 7 different gates? The first one is your buffers or buffer. Okay, second one is your inverter. Third one is your AND gate. Fourth one is your OR gate. Fifth one is your NAND. Sixth one is your NOR. Seventh one is your XOR. Okay, these are the different 7 gates which you are going to study. Okay, so starting off with the buffer. Okay, so what is meant by a buffer? We have seen last module, if your V in is equal to V out, then it is called as your buffer. That is, whatever may be the input, if you are getting that as an output, then it can be called as a buffer. Okay, so how is your buffer represented? So the symbol of the buffer is given as this. Okay, so you have X as an input and Y as your output. Okay, so buffer V in, your output will always be equal to that of your input. So as per your syllabus, there are two symbols which are given. American Standard, this is called as American Standard symbol, and the other one is called as your British Standard symbol, where you will have a box, rectangular box, and this also is your symbol of your buffer. Okay, so I am going to proceed with your American Standard for all the different cases. Okay, so now what is meant by truth table? If you give a table which gives you the output as well as the input value. So in the case of digital, your possible input values are either it will be 0 or either it will be 1. Okay, so if you know that in the case of buffer, Y is equal to, the output is always equal to your input. If 0 is your input, 0 will be your output. If 1 is your input, 1 will be your output. Okay, the third thing what you are going to study is called as your Boolean expression. So X is equal to Y is the Boolean expression in the case of your buffer. Okay, so these are the different, first one is your symbol, second one is your truth table, this is called as truth table, and the third one is your Boolean expression. Okay. Now the next one is your second, third and fourth, that is your inverter and OR gates are called as your basic gates. Okay, so which forms the foundation of your logic gates. So it is also called by another name, which is called as basic gates. Okay. Now what is the other name for inverter? Inverter is also called as NOT gate. Okay, so next one is your second one, that is your inverter. So what is the symbol of your inverter? Inverter means not, it is inverted. If input is X, what will be your output? Output will be Y. Y will be the inverted form of your X. Okay, so this is your symbol of your NOT gate. Okay, now what will be your truth table? So I can write here Y is equal to X. Here I can write Y is equal to X bar. Okay, it is called as a bar. Okay, so what will be your truth table? X, Y. You have two possibilities, either your input will be 0 or either it will be 1. So when your input is 0, your output is going to be the inverted form. So it is 1. If input is 1, your output is going to be your 0. So this will be your truth table. So what will be your Boolean expression? Boolean expression is equal to, output is equal to Y is equal to X bar. This is your Boolean expression of your NOT gate. Okay. So this is your second one, that is your inverter or your NOT gate. Now moving on to the third one. Third gate is called as your AND gate. Okay. So in the case of AND gate is given by the symbol which consists of two inputs and one output. A, B will be your input and Y is your output. AND means it is just like multiplication. Okay, so the truth table is given as, it can be more, inputs can be more than two inputs. Okay, so A, in this case I am taking two inputs, A, B. Now what will be Y? Y will be equal to A dot B or A multiplied to B. So 0 0 0 1 1 0 1 1. So if you have two digits, right, two binary digits, 2 power 2, you have totally 4 combinations, 0 0 0 1 1 0 1 1. So 0 0, what will be your output? Y is equal to A dot B. So wherever you have 0, the output is going to be 0. 1 1 1 to 1, you will be getting 1. So whenever your inputs are high, your output will be high. All other cases, your output is going to be 0. Okay, so that is your AND gate. Now what will be your Boolean expression? Boolean expression will be equal to Y is equal to A dot B. Okay, so this is going to be a Boolean expression of AND gate. AND gate. Okay, now the third basic gate is the OR gate. What you have? So here it is a fourth one. So OR gate. Next one will be your OR gate. So this is your symbol of your OR gate. Okay, Y. So here also I am taking two inputs, OR gate. It's basically the addition. Okay, so A plus B. Now what will be your truth table? If I have two inputs, A, B, Y. So 0 0 0 1 1 0 1 1. So what will be your combination? 0 plus 0 0, right? Whenever you have the input as any input as 1, your output is going to be 1. Okay, so this will be your truth table of your OR gate. Now what will be your expression? Boolean expression Y is equal to A plus B. So this is your Boolean expression of your OR gate. Okay, now so this will be your OR gate. Next one is your NAND and NOR. So the next two gates, NAND and NOR gate, are called by another name as universal gates. Okay, universal gates. So what's the meaning of this universal gates is by using these gates you can form any other, you can derive any other gates. It's just like you are, if you can perform a logical operation, any logical operation using one standard gate, right? So you can perform any operation using NAND and NOR gate. That's why it is called as a universal gates. It's like using a standard gate to perform any operation. Okay. So now fifth one is your NAND gate. So NAND gate is nothing but the opposite of your AND gate. That is inverted form of your AND gate. So if I add a, I am going to use another color. So the structure of your NAND gate will be equal to a small bubble or a small circle towards your output side. So A, B, this is going to be the symbol of your AND gate. Okay, so here if I add a small circle, it's going to be your NAND gate. So the expression is your A dot B bar. Okay, so y is equal to A dot B bar. So what will be your output? Just the inverted form of your truth table is going to be your inverted form. Okay, so y is equal to A dot B bar. So what will be your inverted form? When there is 0, your output is going to be 1, and when both are high, your output is going to be 0. Just the inverted form of your AND gate. Okay, that will be a NAND gate. Similarly, what will be a NOR gate? Just the inverted form of your OR gate. So if I add a NOR gate, right? If I add a circle towards your output, then it is going to be a NOR gate. Okay, so what will be your output here? Just a inverted form. Y is equal to A plus B. So if I can add, what will be a truth table here? So y is equal to A plus B, right? So what will be your invert? Whenever both the inputs is low, your output will be 1. All other cases, the output is going to be 0. Okay, that will be your NOR gate. Now the last one is going to be your XOR gate. There are some exceptional gates to XOR. One is your XOR and XNOR. So here in your syllabus, you are going to study only your XOR gate. Okay. So the symbol of your XOR gate is, so you have a just similar to the OR gate, you are going to add just like this. Okay, A, B. So it's Y. So this is your symbol of your XOR gate. The truth table is going to be, so A, B, Y is equal to A XOR B. 0 0 0 1 1 0 1 1. Okay, so in this case, if both the inputs are similar, your output is going to be 0. Other two conditions, your output will be equal to 1. Okay, if both the inputs are similar, okay, 0 0 and 1 1, your output is going to be low. Other two conditions, the output is going to be high. So the Boolean expression is given by y is equal to A into B bar plus B into A bar, or y is equal to A XOR B. Okay, so this is going to be your Boolean expression. So for now, NAND gate, what is your Boolean expression? Y is equal to A dot B bar. And for NOR gate, your Boolean expression is Y is equal to A plus B bar. Okay, so these are the basic gates which you are going to study in this unit. Now the next topic is going to be your bistables. Okay, so under bistables you are going to study two different topics. One is your RS bistable and the next one is going to be your JK bistable. Okay, so what is meant by bistable? So the name itself signifies, it's also called by different names. It is also called by latches. Modification of latch is flip-flop. Okay, so what is meant by bistable? It has two different states, right? 0 and 1. Okay, so the state will be either 0 or either it will be 1. So bi means 2. Similarly, stable means, okay, which does not change or it remains the same. So what will be your definition of bistable? There will be two states, either it will be 0 or 1. It remains in one state until and unless you have some signal applied. Okay. So it can be, it stores or it gets latched to the one value. If the input is 0, if your output is 0, it will remain in that state and that state until and unless you are going to apply any signal. Okay. It will be latched in that signal. So it can be also called by the name as memory cell. It stores single bit values. Okay. So this is some basic information. Now you are going to study two types of bistable. One is called as your RS bistable. Then three types. Okay. D bistable and JK bistable. So RS, D and JK. Now what is meant by RS bistable? So the first type what you are going to study is called as the RS bistable. Under RS bistable you are going to study two different types. One is called as your NAND RS bistable. That is the RS bistable formed using NAND gates and using NOR gate RS bistable. Okay, so two different types you are going to study. So this is going to be the diagram using NAND gate. Okay, so how will you construct a NAND gate? You are going to take two NAND gates. Okay. So the output of one is fed back to the input. Okay. So this is going to be a reset pin or R and set S. Okay. So whereas in the case of the NOR gate you are going to use two NOR gates. So this is going to be a R, yes, the output of one stage is fed back to that of the input. So this is going to be, in the case of NOR gate, it is going to be Q and Q bar. Okay, just inverted form. Here it is Q bar Q. In the case of NOR it is Q Q bar. Okay. Reset and set. Okay. So what is meant by RS bistable? So R stands for reset and S stands for set. Okay. So these are the two states. Either it will be in the reset state or either it will be in the set state. Okay. So this is a sequential circuit. What is the difference between a combinational and sequential circuit is all the other gates which we have seen before. It's combinational circuit means it doesn't have any feedback. Okay. Whereas in the case of sequential you have a feedback or a closed loop or a storage unit. Okay. So the output is fed back to the input. So this is a example of your sequential storage or sequential memory. Okay. So now let us see in detail what is the first type. Let us see the NOR type, NOR gate RS bistable. Let me draw the diagram once again. Okay. So in the NOR, this will be your Q, Q, Q bar, right? R, yes. Next you are going to give the feedback. Okay. Now what is the, you are using the NOR gate, right? So let me write the truth table of the NOR gate. So only then it will be easy for you to understand the concept. A, B and Y. What is NOR gate? Inverted of your OR gate. So A plus B bar. Okay. So let me check the NOR gate here. right? What is your NOR gate? Expression is y is equal to, oh here I have written a plus b, it is a plus b bar, okay? So what is your truth table? You have the truth table output to be high when you have both the inputs low, all other conditions you have it to be 0. Okay, so your combination 0 0 0 1 1 0 1 1. So your output is going to be high only when you have both the inputs low, and all other cases you are going to be, the output will be equal to 0. That is opposite of your OR gate. Okay, now understood till this? Okay, now let's go for your RS. Now you have to draw the truth table of your RS latch. So this is called as RS bistable or RS latch. Okay, what is the difference between a latch and a flip-flop? I'll tell you. Output Q. So you here also you have to 4 combinations 0 0 0 1 1 0 1 1. Okay, so let me take the condition where your first condition, case 1. You have 4 condition, right? Let me take the first condition as your R is equal to 1 and S is equal to 0. You can take it in any fashion. This is for your understanding what I am taking. R is equal to 1 and S is equal to 0. So the third state I am taking it as the case 1. Okay. So your reset is equal to 1 and S is equal to 0. Now what will be your output you are going to find out. Okay. Now R is equal to 1. So if suppose if R is equal to 1, I am taking R is equal to 1, S is equal to 0. Okay, this is your first case. Now see the truth table of your NOR gate. Whenever the input is 1, your output is going to be 0. No matter what you are getting this from your truth table. Okay, so whenever your input is 1, your output is going to be 0. So definitely your Q will be equal to 0. Right? So now this Q is fed back to your S. Okay. Now when you have both the inputs as 0, what is your output? It is high. Okay, so Q bar will be equal to 1, Q will be equal to 0. So for the first condition, what will be your Q is equal to 0 and Q bar is equal to 1. So when the system is reset, you are going to get Q is equal to 0. Okay, Q bar is equal to 1. This is your first condition. Now let me take the second condition as S is equal to 1 and R is equal to 0. Now let me go for the second condition, right? S is equal to 1 and R is equal to 0. That is called as a set condition. This is called as set condition. First one is called as your reset condition because R is equal to 1. Okay, now the second condition you have S is equal to 1, okay, 1 and R is equal to 0. Now here S is equal to 1. So by the truth table you know that whenever any input is 1, your output is going to be 0. So for this case now your Q bar will be equal to 0. Okay, no matter what is the other input. So Q bar now it is fed back, it will be 0. Now 0 0 the output will change to 1. Okay, now it will be in the set condition. So what is the condition now? Q is equal to 1, Q bar is equal to 0. Okay, so now what is the value for Q? It is in the set condition. Now Q will be equal to 1. Okay, now you have got the second one. Now let me move on to the case 3. Let me take S is equal to 0 and R is equal to 0. Okay, first option 0 0. Okay, both 0 0. Now what will be happening? Now S is equal to 0. Let me take another color. S is equal to 0. R is equal to 0. Now here sequential circuits also there is one more property. It depends on the previous output also. Right. Previously your Q was equal to 1. Okay. So Q is equal to 1. Now your S is equal to 0. So what will be your output? Output will be equal to, now I am taking the previous stage. I am taking previous stage, your output Q was equal to 1. Now present state S is equal to 0. So when this 1 comes here, what will be your 1 0? You will be getting the output will be equal to 0. Because the sequential circuit depends on the past output also. Okay. Now output is equal to 0. This 0 is fed back here. Now what will be your 0 0, what will be your output? 1. That is, here the previous state was 1. Now the present output is also 1. Previous output was 0. The present output is also equal to 0. That is, Q is equal to 1. It is remaining in 1 and Q bar is equal to 0. Means what? There is no change in the output, or it holds the previous value. Okay. So it is called as previous value or no change in the output. It remains the previous value. What was the output? It remains in that same value. Okay. So these are the three conditions, three output conditions. Now, what is the disadvantage of your RS flip-flop is there is a condition which is undeterminate or undefined. It is called as a race condition, where you have both the inputs as 1. So case 4, if both the inputs as 1, let us check. Okay, R is equal to 1, S is equal to 1. Now what will be the condition? Now for the last one we have R is equal to 1, S is equal to 1. See here, whenever your input is 1, your output will be remaining in 0. Means what? Your Q also will be in 0, Q bar also will be in 0. While the complement of Q is called as Q bar. It cannot be the condition, right? So 0, 0 is an exceptional. It cannot be always. If Q is 0, the Q bar has to be 1. It is not true. So this condition is given by X. It is called as a race condition or undetermined condition. The system doesn't know what to do. So this is overcome by means of using JK flip-flop. Okay. That's why you go for JK flip-flop. Understood? Okay. So this is your truth table of your RS flip-flop. So for your case, in your syllabus, you have to study this diagram and this truth table and the diagram of your NAND gate. Okay. So the NAND gate and NAND gate also I will be explaining it for just for your understanding. Okay. So the next structure is your NAND gate. So how will you construct your RS using your NAND gate? So here you have a NAND gate. Here also NAND gate. What are the two inputs? One is your R and the other one is S. What is the difference between your Q and Q bar? Just transverse it. So here you will be getting Q bar. Here it will be Q. I'll tell you the difference, why it has been made. Now you have to give your feedback signal. Okay. So this is your structure for your NAND gate. Since we are dealing with the NAND gate, let us write the truth table of your NAND gate. NAND gate truth table. Okay. A, B and Y. 0 0 0 1 1 0 1 1. So what will be your output of your NAND gate? Whenever both the inputs are high, you will be getting the output to be 0. All other cases, whenever your input is 0, you will be getting any one input is 0, you will be getting it to be high. That is the opposite of your AND gate. Okay. Now we have to construct a truth table of your R, S, Q. You can write it in any way. S, R, Q also is okay. So 0 0 0 1 1 0 1 1. So in the previous case, what was your condition? Okay. So it is just opposite here in the case of using NAND gate. See here. So here it was 0 0, there is no change. But here it will be ulta. 1 1 will be your no change condition. Okay. And 0 0 will be your race condition or undetermined condition. Now here also set means Q will be equal to 0. Okay. And reset means your Q will be equal to 1. So opposite of your OR gate will be your NAND gate truth table of your RS NAND gate. Okay. So this is your condition. 0 0 in the case of OR gate it was no change. Here it becomes the undetermined case. 1 1 will be your no change. Here it will be 1 1 will be your undetermined. So in the previous case set was when Q is equal to 1. Reset was when Q is equal to 0. Here it is just ulta. Okay. Now let us check the conditions. So similar to the last one, let us see the first condition. So when if I take S is equal to 0 and R is equal to 1, first condition. So S is equal to 0, R is equal to 1. So by means of your truth table of NAND gate, you know that if any one input is equal to 0, your output is going to be definitely 1. Okay, so here your Q will be equal to 1, right? So that Q is fed here. When both the inputs is 1, your output is equal to 0. So Q is equal to 1, Q bar is equal to 0. Therefore, now you have got Q is equal to 1. For the condition R is equal to 1, this is done. Okay. Case 2. If S is equal to 1 and R is equal to 0. Okay. S is equal to 1 and R is equal to 0. Now, which R is equal to next one. So, R is equal to 0, S is equal to 1. So, you know by truth table, if any one input is equal to 0, your output is equal to 1. So, here the input is 0. Definitely your Q bar is going to be 1, right? Q bar is 1. That 1 is fed here. So, 1, 1, your output is going to be 0. Okay. So, in the case 2, Q is equal to 0, Q bar is equal to 1. Okay. It is satisfied. Q is equal to 0. Now, case 3. Let us check the unchanged condition. So, in this case, S is equal to 1, R is equal to 1. It is the unchanged condition, right? Now, S is equal to 1, R is equal to 1. Since it is a sequential circuit, since it depends on the previous output, so here you have Q bar is equal to 1 in the previous case. Now, if I give that as input here, 1, 1, what will be the output? Output will be in 0. Okay. This 0 will be fed back here as the input. So 1, 0, what will be your output? It will be equal to 1. So both the outputs are same. There is no change. Q is again remaining in 0 and Q bar is again remaining in 1. So there is no change. So that's why you have this condition to be satisfied. Now you have the indeterminate stage. In this case, it is S is equal to 0 and R is equal to 0. If any of the inputs is equal to 0, definitely your output is going to be 1. So in this case, both will be equal to 1, which is not possible because Q bar is the complement of Q. Okay. So you have this as your undetermined or race condition, which will be overcome by the JK flip-flop. Okay. So this is your RS bistable. Now next you are going to study about D flip-flop. So now this is called as latch or bistable. Okay. So if I am going to add a clock, okay, then it is called as flip-flop. Since the truth table was not clear, let me show you once again the RS NAND gate flip-flop. So 0, 0 was your race condition or indeterminate condition. 0, 1, Q was is equal to 0. If reset is 1, Q was 1. And 1, 1, there was no change. Whereas in the case of NOR, that is RS bistable, see here it was opposite. 0, 0, no change. So it is just interchange here. 0, 1. When S is equal to 1, Q was equal to 1. When R is equal to 1, Q was equal to 0. The opposite of this. Okay. 1, 1 was the indeterminate state here. Here it was no change. Okay. The next bistable what you are going to study is your D bistable. Okay. It is also called as delay or data. So D bistable. So what is meant by D? D stands for delay or data. So it is also called as delay or data bistable. Okay. So how many inputs you have? It has two inputs. Okay. So one is your D and the other one is going to be your clock. So these two are your inputs. Sometimes in some cases you can give additional inputs like preset and clear. So it is called as preset and clear. Preset is normally given by PR and clear is given by CLR. So this stands for clear, which is used to clear and preset the value. Means set and reset the value. Okay. That is the use of these two inputs. Okay. Now I'll draw you this structure or the symbol of your D flip-flop. So it has two inputs. One is your D and the other one is called as your clock. Okay, so here it is, clock is triggered during the rising edge and you have the output Q. So it is delay or data. Whatever is the input, you will be getting the same as the output but with a certain delay. So if I can tell this as your transient data to be stored. So this is your transient data to be stored. This will be the data output data that is clocked during the rising edge. Okay, now if I can show you by means of timing diagram, if this is your input and if you have this as your data. Okay, so this will be your data input or your D. Okay, so now the same data will be given to the output only when you have your clock pulse. So during the rising edge, this is your rising edge, if this is your clock signal, only during the rising edge the same data will be transferred. Okay, so this will be your data input transferred. So this is your use of D bistable, or it is called as your delay bistable. Okay, the next flip-flop or the next bistable what you are going to study is your very important bistable, that is called as your JK bistable. So what is the advantage of your JK bistable? It is just similar to that of your RS flip-flop, but what is the difference? The indeterminate state was rectified in this JK flip-flop. Okay, so let us see what is that 1 stands for. Okay, so it consists of two inputs. One is J and other is K. So it is similar to S and R. So S stands for J and R for in the place of K. Okay, now just similar to that of the D flip-flop, it consists of two additional inputs. What are the additional inputs? One is your preset and the other one is your clear. PR and clear. Preset and clear signal. Okay, then you will be having your JK as your input. You will have your clock as your another input, and output will be Q and Q bar. Okay, so this is going to be your input and the output parameters. Now if I can draw the diagram of JK flip-flop, let me take the diagram of using NOR gate. Okay, RS flip-flop using NOR gate. In that I am going to just modify your diagram. So the same RS flip-flop I am going to modify it as JK flip-flop. So let us draw first your RS flip-flop. Okay, so you will have a NOR gate, second NOR gate, right? This will be your Q and this is going to be your Q bar. You have two inputs, one is your R and the other one is your S. Okay, now what is the next thing you have done? The output will be fed back to the input. Okay, so this is your RS latch or RS bistable which we have drawn before. Now if we extend this with a certain slight modification, so we are going to extend this. Okay, and we are going to connect it to two AND gates, because we are going to give the clock input signal as one of the input to the AND gate. So this is going to be your clock signal, input signal. So R, so here it is K, here it is J. Now in addition to this you are going to give, so this will be your additional, let me do it with another color. Now the other additional feature is that you are going to connect a feedback from Q to your K, similarly from Q bar to your J. Okay, so this is your structure. So what will be, this will be your RS flip-flop, and this is going to be your modification. So this is your complete structure of your JK flip-flop. Okay, so now the truth table of the JK flip-flop is given by JK. If I can give it as Q, the same truth table of your RS flip-flop, the only difference is what? Your 1-1 stage is being removed from your indeterminate state. So 0 0 0 1 1 0 1 1. So for in the case of NOR, what was your condition for your 0 0? There was no change. 0 1, if k is equal to 1, means k is equivalent to that of your R, right? If reset was equal to 1, Q was equal to 0. If set was equal to 1, in this case it is similar to J. So Q is equal to 1. So in the previous case 1, 1 was indeterminate. But in this case you are going to get a condition that is called toggle. It switches between Q and Q bar when we change the clock. So during one clock you will be getting it as 0, means the other clock you will be getting it as 1. So it changes of the changes the values. Okay, so this condition is being defined. Okay, so this is one truth table, and you have another truth table which is given, that is for your preset and clear. Preset and clear, what is your output? Okay, yeah, let me take the output as okay, y. Now so you again, you here, if I give you condition 0 1 1 0, so when preset is equal to 1, your value of Q will be always set to your predetermined value. Let it be Q is equal to 1. Now when the clear is equal to, when you are giving a clear, your output Q will be cleared with 0 value. Okay, it will be cleared with no data. So before the start of the any experiment or any logic operation. Okay, so let us check the condition now. The same working principle goes with that of your JK flip-flop. So let me take the first condition. When case 1, if J is equal to 0, K is equal to 0. So what will be the condition if J is equal to 0? So your first condition, J is equal to 0, K is equal to 0. So what is the case of your AND gate? AND gate is your multiplication. If any one input is equal to 0, right? A, B, Y for AND gate, A dot B, 0 0 0 1 1 0 1 1. So if any one input is 0, your output is going to be 0. If any one, both the inputs are 1, only then it will be high. So in this case both the inputs are 0. So what will be your value of your AND gate output? It will be 0. That is nothing but R will be equal to 0, S will be equal to 0. So R is equal to S equal to 0. We have already found out the explanation. So there will be no change. Okay. So this condition is called as no change condition. Now what will be your case 2? Case 2, if J is equal to 0, K is equal to 1. Second condition, if J is equal to 0, K is equal to 1. So what will be this condition? If J is equal to 0, your output is going to be 0. So okay, so second S is equal to 0. If K is equal to 1, what will be the value of Q? What will be the value of AND gate? You have one input coming from here, right? Feedback. So it will be equal to Q. Okay, 1 into Q, you will be getting the value as Q. So Q, what are the options you have? You have either it will be 0 or either it will be 1. If it is 0, your output is going to be 0. So it's invalid, right? Again, R will be 0, S will be 0. So it is no change. Now the next option is Q will be equal to 1. If Q is equal to 1, your AND gate will be equal to, output will be 1. So I can write the next condition 1, 0. Now reset is 1, set is equal to 0. So you will be getting, what will be the output? Output Q will be equal to 0. Same as that of the explanation previous one. Now what is the next condition? So Q will be equal to 0. Okay, q bar will be equal to 1. Now what is the third condition? If j is equal to 1, k is equal to 0. So if j is equal to 1, now the third condition you have j is equal to 1, k is equal to 0. So you have one input here is 0. So obviously your AND gate here will be 0. So R will be equal to 0. But in the case of j, you have the input as 1. Now you will have to consider the next input coming from your q bar. So q bar will come as the another input. So q bar has two options, whether q bar can be 0 or it can be 1. If q bar is equal to 0, again here you will be AND gate output, you will be getting it as 0. So the condition goes to 0 0, there will be no change. Now the applicable condition is if q bar is equal to 1, 1 into 1, the output of AND gate will be 1. So here you have an option 1. So now your input of your RS is 0, set is equal to 1. So what will be your condition? Q will be equal to 1, Q bar will be equal to 0. Now you are going for your last condition. Okay, when both is equal to 1, when j is equal to 1, k is equal to 1. Now what will be the condition? Here also you have 1, here also you have 1. So in both the cases it will depend on your previous means your feedback, right? Q bar value also you will be getting, q also you will be getting. So let me take the previous state. So previous state, what was the value? So q is equal to 1, q bar is equal to 0. So q was equal to 1, q bar was equal to 0. So q bar will come here. So 1 into 0, your AND gate will be 0 now. Okay. So your next condition is s is equal to 0. Now you have q is equal to 1, that will go here. 1 into 1 you will be getting 1. So your next state is r is equal to 1. Now what is the condition? You have got r is equal to 1, s is equal to 0. If r is equal to 1, s is equal to 0, what will be your value? Q will be equal to 0 and q will be equal to 0 and q bar will be equal to 1, right? Now it has changed from the one previous state to the next state, that is q has become 0 and q bar has become 1. So it is called as toggling. Okay, now what is the condition? Q when j is equal to 1 and k is equal to 1, you have got q has changed from 1 to 0. Q bar has changed from 0 to 1. Now the value of q is equal to 0, q bar is equal to 1. Now what will happen for the next clock pulse? What will happen? Now q0 will go to your k and your q bar 1 will go to your j. Okay, now what will happen? When 0 will go to your k, now k becomes 0. So r here becomes 0. Now q bar has become 1, right? When that 1 goes here, you will be getting s is equal to 1. The state changes from r is equal to 0, s is equal to 1. So r is equal to 0, s is equal to 1. Now what will happen? Q will be again changing to 1 and q bar will change to 0. See here, next for the next clock pulse, what happens? Q has changed to 1, q bar has changed to 0. Means it is toggling. It keeps on toggling as the clock is applied from 0 to 1. So it is defined. Undeterminate state is eliminated. Now for JK flip-flop, you have two examples given. One is your counter and the other one is your shift register, which we will be seeing in the end of this module in detail. Okay. If this video was helpful, do like, share and subscribe.